We often assume reading is a smooth, linear process. You process the text sentence by sentence, steadily building a coherent picture in your mind. But the moment you stop reading for pleasure and start searching a document for a specific piece of information, that linear progression breaks. Searching a text operates as a distinct cognitive engine, entirely separate from continuous reading. Instead of passively absorbing the next word, your brain is forced into a continuous loop, evaluating whether the sentence you are looking at right now satisfies the requirements of your immediate goal. While continuous reading is a relatively low-effort absorption state, document search is a highly active, biologically expensive cycle of relevance assessment. How well you remember a piece of text is dictated entirely by the constraints of the task you are given while reading it. This bar graph maps the literal footprint of human attention across a 35-paragraph text. Notice the behavioral discrepancy here, two radically different patterns of physical interaction with the exact same document, driven solely by the type of question the reader was answering. The isolated dark bars represent a low-level, specific search, a reader looking for a single fact. The widely distributed light bars represent a high-level, inference-based search. Testing later revealed that readers who performed the high-level search encoded a demonstrably deeper, more robust long-term memory of the document structure. Retrieving a single, targeted fact is incredibly efficient, yet it is the slower, high-friction task that yields vastly superior comprehension. The data shows us exactly why this happens. To understand the mechanics of this discrepancy, we have to examine the methodology behind the data. Researchers gave university students a complex 2,500-word physics text. The students were divided into two groups. Half were given a specific fact retrieval question to answer. The other half received a broad comparative question. To map exactly where these students focused their cognitive resources, researchers needed to track their attention down to the millisecond without external eye-tracking hardware. They used software called Select the Text. As you can see on this screen, the main body paragraphs are deliberately obscured by asterisks. Only the section headings are visible. To read a paragraph, the subject must intentionally click on it. This physical action unmasks the text. Simultaneously, it records the exact duration of cognitive focus spent on that specific block of information. Through this interface, abstract cognitive allocation is converted into a literal, trackable footprint. Let's return to the data and analyze the physical footprint of the low-level search. The prompt for these subjects was simple: identify the specific type of particle used in a physics experiment. Look closely at the massive spike of the dark bar located at paragraph 21. This is the signature of a hyper-targeted extraction mission. The reader scans the text, locates paragraph 21 where the particle is mentioned, extracts that singular fact, and stops. This process demands very little of the brain's working memory. It successfully produces a correct answer, but it leaves behind an entirely isolated memory trace. The low-level search is an incredibly efficient mechanism for retrieving data, but requiring zero integration with the surrounding text, it completely fails to build a connected structural map of the document in the reader's mind. Contrast that targeted efficiency with the behavioral footprint of the high-level question. These subjects were asked to compare Thomson's atomic model with Rutherford's competing model. This resulting graph shows a distributed wave of attention. The light bars are scattered widely across the entire horizontal axis. Notice these specific structural clusters. The subjects spent heavy review time around paragraphs 17 through 20, and then again around paragraphs 30 through 33. This behavior illustrates a concept developed by psychologist Walter Kinch called the macrostructure. A text operates as a network of propositions that condense and connect detailed information, rather than a simple list of facts. The high-level prompt forces readers to move past explicit surface details. They must synthesize multiple separate concepts into a broader mental model of the situation. By requiring the reader to evaluate and bridge distant nodes of information, the task deliberately converts isolated facts into systemic, structural comprehension. The engine driving this specific behavior is known as the TRACE model, or Task-Based Relevance Assessment and Content Extraction. The model maps a strict cyclic loop. The searcher establishes a goal representation, assesses the text for relevance, extracts the information, and then repeats the process. The critical bottleneck in this entire operation is the hard limit of human working memory. To answer a comparative question, you must hold intermediate data active in your working memory buffer while scanning entirely new paragraphs. New incoming text competes for space, easily overwriting your original goal, causing you to lose your track entirely. Succeeding at this task requires co-activation, forcing your mind to successfully hold two distinct, distant pieces of information active simultaneously. This forced co-activation is the exact physiological mechanism that reinforces neural connections in your long-term memory. The high resource cost of juggling intermediate data serves a precise purpose. That cognitive friction is the mechanism that engineers deep comprehension. If we zoom out from the trace model, we can categorize exactly how different types of instructional prompts route our cognitive processing. The effectiveness of a question relies on two main parameters: the direction it forces you to look and the breadth of its target. This diagram maps these parameters into 4 quadrants: forward or backward directed, and specific or general targets. The most cognitively demanding quadrant is the backward directed general question. These prompts mandate mental review. They force the searcher to retrieve already processed data from memory and actively restructure it to fit a new, broad framework. In cognitive psychology, friction is a biological requirement. Resource-consuming, backward-directed questions force the deep integration of complex material. This brings up an obvious practical issue. External prompts are useful, but how do experts navigate complex text naturally without inserted questions guiding them? The answer lies in the PREG model, which revolves around a state called cognitive disequilibrium. Cognitive disequilibrium occurs when a reader encounters a computable discrepancy between an explicit statement in the text and their own internal prior knowledge structure. Experts possess enough baseline knowledge to detect these structural discrepancies. When they spot a conflict, the disequilibrium acts as an internal trigger, prompting them to self-generate their own high-level searches to resolve the tension. Novices lack that baseline. They do not have enough prior knowledge to realize they are in a state of disequilibrium, meaning they never trigger the search cycle. For complex technical education, passive reading is a myth. To build resilient long-term memory, instructional systems must be deliberately engineered to force relevance-based evaluation and require the synthesis of multiple, distant nodes of information.